National Museum of Natural History. The students of T.C. Williams High and I will be part of your guides through the new Geology Gem and Mineral Hall here. This is an interactive national field trip. Get your questions ready. Phone, fax, or email them, and we'll be right back at you through the magic of modern computer technology. But first, let's take a look at the introduction to this field trip with Robert Sullivan, our Associate Director for Public Programs, and Jeffrey Post out in the front Harry Winston Gallery. Guys, are you there?
Yeah, we're here, Sorena. Thank you. I'm here with Jeff Post, of course, our curator of gems and minerals and the guy who knows more about rocks than anybody else I know. And we're going to do something odd right now. We're in the middle of this great hall of gems and minerals, but we're going to convince you that gems and minerals and crystals are not extraordinary, but are everyday things. Isn't that right, Dr. Post?
In fact, you use gems and minerals every single day of your life.
Every single
day.
day.
I'll bet you this morning you used several minerals.
I don't believe it.
Just getting ready to come to work this morning.
I can't believe I did.
Well, in fact, one that I'm sure that you benefited from was this mineral right here.
Nope, I didn't use this mineral this morning. I'm absolutely sure.
Well, but you used what was in this mineral. This is the mineral fluorite, which is the source of fluorine. Fluorine being for fluoridated water, fluoride in toothpaste. So if you brushed your teeth or if you washed this morning or had a drink of water, this was a mineral that was very important to you this morning.
That was awful rough on my teeth, Jeff. What is it in this mineral that makes it good for teeth?
It's the fluorine. And the fluorine is used to make the fluoride compounds that are in toothpaste.
Okay,
and that keeps you from getting cavities.
I'm bored with this now, Jeff. What else have you got here?
Okay. Well, I'm assuming after you brushed your teeth, you probably put a little bit of underarm deodorant on this morning. At least I'm hoping you did.
I forgot to do that, actually, but tell me what I should
have
have done.
This is the mineral zircon, and from the mineral zircon, we get the metal zirconium, and zirconium compounds are one of the main ingredients in underarm deodorants.
So you at your home, you just kind of take this and put it under your arm?
Actually, if you just put it under there and kind of hold it there, you have no problem for the rest of the day.
That's very handy mineral. What else have you got there?
Well, eating your breakfast, perhaps put a little salt in your oatmeal or on your French fries, whatever it might be.
I put just about that much on there.
That's a big crystal of salt. The mineral name is halite, sodium chloride. And most of the salt that we use is in fact mined from underground. It's a mineral, just like this crystal here.
Well, I wouldn't try this at home, but it actually does taste just like salt.
And it's cleaner than it's ever been before.
I guess it is.
Well, another very important metal that we use every day, of course, is copper.
Copper.
Copper on pennies, copper in wiring, copper in
And I bet
plumbing.
there's some copper nearby here somewhere.
We happen to have a spectacular specimen of copper. This specimen of copper came from a mine in northern Michigan. This is a piece of called native copper. That is, it's found in its natural state as essentially pure copper metal. This was found sandwiched between layers of shale in a mine, and in the process of blasting to remove the ore, this piece was removed and somewhat crumpled up as we see it here now. This piece of copper formed about 1 billion years ago when the continent of North America was starting to sort of being pulled apart or rift apart, and the resulting volcanism placed these copper deposits into northern Michigan. Now, we've got also in this gallery one of the most famous geological specimens in the entire Smithsonian Institution, and in fact, the most famous diamond in the entire world. And that is, of course, the Hope Diamond. The Hope Diamond is our most visited object at the Smithsonian Institution. Everybody comes wanting to see the Hope Diamond. And I think most people coming in expect to see this big basketball-sized diamond. Well, in fact, people are rather surprised to see that, first of all, it's not the world's largest diamond. It's about 45.5 carats, so that's a pretty good-sized diamond, but certainly not the world's largest. And also, it's a blue diamond. Typically, we're used to looking at diamonds as being colorless, but in fact, if there's a trace impurity of the element boron present, we can then get a blue diamond. And part of what makes the Hope Diamond so unusual and so special is that it's the world's largest blue diamond. Now, another reason why the Hope Diamond is a very important stone is it has a very interesting human history. The diamond came out of India in the early 1600s, then was sold to King Louis XIV, passed through the hands of many other kings and queens, eventually was purchased in this century by the jeweler Harry Winston in New York, and then donated it to the Smithsonian Institution. Now, one of the intriguing stories about the Hope Diamond is that many people believe that there's a curse attached to the diamond. Well, we don't believe in curses, but it is a very fun story to tell, and in fact, for us, the Hope Diamond has been a great source of good luck. Well, the Hope Diamond is a good example of a gem or a mineral in this that has many different reasons for it to be interesting. And that's one of the things that we want to think about through this entire field trip. So let's take a look at some of the other specimens that we're going to be seeing today and talk about why they're important in many different ways. We've moved into the National Gem Collection Gallery, home of many of our finest gem pieces and some of the most popular objects in our entire collection. Many of our visitors come expecting to be impressed by the gems, which of course are cut and polished examples of mineral crystals. However, when they pass through the door into the Minerals and Gems Gallery, they are surprised, even astonished to see that the natural mineral crystals in many ways are even more fascinating than the gemstones are. For example, a specimen such as this one, the beautiful blue crystals of amazonite, a variety of the mineral microcline, and smoky quartz crystals, is a natural creation of the earth. This specimen has not been altered or changed in any way. It simply was dug out of the ground, cleaned, and brought to the museum. It looks like a sculptural piece. In fact, many of our visitors truly believe that specimens such as these are being created here at the museum and put on display as art objects. In fact, it's a natural product of the earth. And so as we're walking through the exhibit and looking at many of the specimens that we have on display here, one of the ideas that we like to keep in mind is that we are looking at natural specimens that have formed in the earth. Now, it's fun to look at these as beautiful objects, and truly they are, and that's part of the reason they're here in this display. But in addition to looking at them as beautiful things, we'd like to try to remind you to also think of them in terms of what they can tell us about the earth. Certainly a scientist, his interest or her interest would be in looking at a specimen like this and trying to understand what can this specimen tell us about where it formed, the conditions under which it formed, what has happened to this specimen in the earth since it first began to form crystals like these. So to scientists, every mineral has a story. And one of the things we'd like to try to do as we look at some of these specimens is see if we can figure out what that story is and see how those stories in sum total can tell us about our earth. So in addition to the aesthetics of many of the specimens here, clearly one of the interests that we have is trying to discover their stories and learn something about what they can tell us about the earth. Another facet of many of our specimens that I think visitors find very interesting and is part of their story is the human story that they can tell us. Many of our specimens, especially our gemstones, have been owned by very interesting people through time and have a fascinating story that they can tell us. For example, the Hooker Emerald. This is an emerald that was given to us by Janet Annenberg Hooker, who is also a major donor to this entire exhibit hall, which is why it's called the Janet Annenberg Hooker Hall of Geology, Gems, and Minerals. This is an emerald that she gave us back in 1977. And it's a very interesting emerald because at one time was an emerald that was worn by the Sultan Abdul Hamid II of the Ottoman Empire. And he wore it on his belt buckle. And this emerald was then purchased by Tiffany's, and they cut out of the heart of this emerald the emerald that we have here today as the Hooker Emerald. So the connection that many of our pieces have to people and to our history is part of what makes them fascinating. Minerals and gems are not diminished with time. They tend to stick around and accumulate stories, accumulate history. And it's fun to learn about those stories and those histories. Now finally, another perspective that we'd like to have on our specimens as we go through the galleries is to remember that many of these minerals are also important to us economically. For example, we have the spectacular group of crystals of a mineral called stibnite. A stibnite specimen such as this is certainly a beautiful thing to look at. The crystals resembling perhaps a modern sculpture, art piece. However, to the miners in Japan, where this specimen came from, this was the ore that they were seeking. It's the ore of a metal known as antimony. Antimony is used to harden lead for ammunition, bullets, that type of thing. Also, compounds of antimony are used as fireproofing on clothing and other fabric materials. So it's a very important metal for us, and that metal comes from this particular mineral, stibnite. A lot of the minerals that we'll see throughout the gallery are ores of various metals. All of our metals, most of the raw materials that we need in industry today, in fact, come from mineral specimens. And many beautiful specimens such as these never see the light of day. They're blasted, dumped into the crusher, and the metals extracted from them. And so in some ways, the beautiful specimens are very unusual in that they were preserved from this process. But keep in mind that, again, every day, all of us make use of a great many products derived from minerals, and that's certainly one of the stories that we'd like to try to keep in mind. So, as we go through the galleries here in the new Gem and Mineral Hall, what we'd like to keep in mind is that there are many ways for us to look at and appreciate minerals. And let's take, for example, one more specimen. This group of pyrite crystals is just the way it was found. These are the natural shapes of the crystals. Again, many of our visitors find that hard to believe. Clearly, it's a specimen that can be enjoyed because of its aesthetics. However, it also is mined as an ore of iron, and in some cases sulfur, for making sulfuric acid. And to a scientist, he or she would look at this specimen, looking at the crystal shape, and be able to learn something about the conditions under which this particular mineral was formed, the temperature, the concentration of the solution. So it has many stories to tell, and we can appreciate it in many different ways. So we look forward to now going back to some students who are looking at crystals that they find in their own part of the country.
So, T.C. Williams, say hello to Stark County, Ohio. Hi, guys. Hi. You out there? Okay, do we have some questions from Stark County? Good morning. Clayton.
Hi.
Hi, Chrissy.
I was wondering, why does the impurity of the Hope diamond make it so rare? And is it the only blue diamond?
I'm gonna fling that back to Jeff, who's our blue diamond expert. Jeff, did you hear the question?
No, Sorena, I couldn't hear the question. What is the question?
Why is the blue diamond blue, and is it, Chrissy, you want to repeat the question? Or excuse me, you're not Chrissy, but could you repeat the question?
Yeah. Why does the impurity of the diamond make it so rare, and is it the only blue diamond?
Okay, why does the impurity in the Hope diamond make it blue, and why is it so rare?
Well, the impurity in the Hope diamond that makes it blue is boron, and boron is a very unusual element. We don't find it in a lot of rocks in the earth, but in the area where the diamond is forming, there is, in some cases, boron present, and so a few boron atoms are enough to color the diamond blue, and it's the light interacting with the electronic structure of the boron atoms in the diamond that cause the color to be blue.
Great. Anybody out there in Stark County know what the main minerals collected in Ohio are? Anybody know? Clayton, do you know?
Halite and gypsum.
Good guesses. I don't happen to have any of those guys. I have the more commonly collected ones. Anybody know what the most commonly collected minerals in Ohio are? Okay, well, let me show them to you here. Here's calcite, fluorite, and celestite, a beautiful celestial blue. You'll hear more about this one later. Jeff, I've got a neat concretion here from Ohio. It's an old worm tube that's covered with beautiful pyrite crystals. Wow, the darn thing is almost 3 feet long. Take a look at this. I think you've got a concretion to show us now, right?
Well, Sorena, we've got a concretion here in the Harry Winston Gallery as well. It looks a little different than the one that you were showing, but this is a concretion that came from a sand quarry in Fontainebleau, France, near Paris, France. Some people think it looks a little bit like a couple of sumo wrestlers going at it, or perhaps the old Michelin tire man in the commercials, but in fact this is a naturally formed concretion. This originated as sand on a beach about 35 million years ago. The beach sand was eventually buried and then was, through time, uncovered by erosion processes such as water and wind. The sand then was quarried for use for making glass and has been quarried in this location for about 300 years. In one part of the quarry, apparently groundwater flowing through the sand deposit had silica in it, and that silica was deposited as a glue, basically gluing the sand grains together, forming this very whimsical shaped concretion. So, Sorena, you got any other questions back there?
I think we've got a Washington question, right?
Yeah. Does age have any effect on the color or the size of a mineral or a rock?
No, color is something that's independent of age and size, with one exception, color that's induced by radiation, which can intensify with time. Any questions from Ohio?
Hello?
Chrissy, you're on the air.
Yeah. Why doesn't Ohio have the same quality of minerals that you have in your collection? For example, why don't we find emeralds or topaz in Ohio?
Well, okay, those two minerals are very rare worldwide. You need to bring rocks of unusual types together, and that usually happens in unquiet parts of the world, places where plates come together and bring rocks that might ordinarily be in the mantle in contact with those in the crust. And that geological situation just hasn't happened in Ohio. Do we have any 800 calls this morning? Not yet? Okay. What we're going to do then is take a look at some of the rarest and most fabulous gems that we have that aren't necessarily on display. We've got some pretty good ones in the back room, and I think Jeff is going to show us some of those.
Okay, thank you very much, Sorena, and welcome everyone to the Blue Room here in the Department of Mineral Sciences at the National Museum of Natural History. This is our secure storage area for the mineral and gem collection. We have in the glass cases around me many of our finer exhibit quality mineral specimens. We have also here the gem vault with about 10,000 gems from the National Gem Collection. All told, we have about 300,000 specimens in our collection here. But the bulk of them are materials that are primarily for scientific research, but we have pulled out a few of the special pieces and stored them here. We would prefer that scientists are not taking some of our best crystals and knocking little chips off of them. One of the fun things about being back here in the Blue Room is that you do get to see some of our more interesting specimens. For example, some of our large crystals and our gem pieces. And take, for example, this lovely crystal of aquamarine. This is the mineral beryl. This color is used as the gem material aquamarine. This is a natural crystal. This is the way it came out of the ground. Not very practical for use as a gemstone in this form, but if you take a crystal like this one, or this smaller beryl crystal, the smaller aquamarine crystal, if we take a crystal like this one and a skilled craftsman were to cut and shape and polish it, they could make a gemstone such as this aquamarine gem. And we have then a gemstone which can be set in a piece of jewelry or used as other items of decoration. But a gem is simply a cut and polished version of a natural mineral crystal. This is what comes out of the ground. Once it has been cut, polished, and shaped, this is what we then call a gemstone. Now, in the National Collection, we get quite a variety of very interesting gemstones, and many of them come to us set in pieces of jewelry. And we have a few rather unusual pieces of jewelry that have made it into the collection over the years. For example, let me pull something out of the drawer here. This is a rather unusual piece, not something you'd probably see worn at most parties these days, but this is an owl that is crafted out of diamonds and pearls and a little bit of gold. And we also have another kind of interesting piece. This piece actually won a design award for jewelry a few years ago. It can be worn as a brooch or a pendant. And what's kind of fun about it is that it actually opens up and reveals a beautiful selection of colored diamonds, ranging from yellows to oranges to brown. Okay, this piece is called the pomegranate. So one of the other kind of fun things about gems, besides the fact they come in all sorts of interesting shapes and sizes, is that they also come in quite a range of colors, which is why gems are probably as popular as they are. If all gems were colorless, clearly we wouldn't be nearly as excited about buying gemstones. But for example, we have a gem such as this aquamarine. This aquamarine is a cut and polished version of the mineral known as beryl. Beryl is a beryllium aluminum silicate, and beryl in its pure chemical state is colorless. However, if as a beryl crystal is growing, it incorporates a few atoms of iron as impurities. Those atoms will interact with light entering into the crystal to give us the shades of blues and greens that we prize then as the gem material known as aquamarine. But the story gets more interesting. In fact, this is also a gem variety of the mineral beryl. This very bright green gemstone you may recognize as emerald. Emerald is beryl that has trace impurities of the element chromium. Again, just a few atoms of chromium trapped in a beryl crystal as it's forming are enough to color it this deep green color. And instead of chromium or iron, the beryl crystals trap a few manganese atoms, then we get the lovely pink shade that is known as the gemstone morganite. And in fact, there's more to the beryl gem family. Sometimes beryl can have iron in a slightly different chemical state than in the aquamarine, and the result is a golden yellow colored gemstone known as heliodor. So we have a complete family of gems, all from the mineral beryl, the only difference being slight trace impurities of different chemical elements that were incorporated in the crystal as it grew. So you end up getting blue, green, pink, and gold colored gems just because of slight differences in impurities. But all of these are the same mineral, beryl.
Hi, I'd like to remind you folks out in Cyberland of our 800 number and also our email address. It's outreach@bsu.bsu.edu. We've had a look at a mineral made of a very rare metal, beryllium, that makes these beautiful beryls. Now, Jeff, I think we're going to turn to a more common metal that nonetheless makes two of Earth's most beautiful gemstones. Is that right?
There's another family of gems that I think most of you will be familiar with, and it's the mineral corundum. Corundum is aluminum oxide, and just like the beryl, in its pure state, corundum crystals would be colorless. However, if it incorporates some purity atoms as the crystals are growing, we can get some interesting colors. For example, if the impurity atoms are chromium, so there's just a few chromium atoms in the corundum crystal, that can color the crystal the deep red color that we prize as ruby. If, however, instead of chromium atoms, we have a few impurities of iron and titanium, then we get crystals that are deep blue and cut gems that we call sapphires, such as this sapphire from Sri Lanka. So we have sapphire and ruby, both gem varieties of the same mineral, that is the mineral corundum. Now we usually think of sapphires as being blue. However, sapphires, depending upon the impurities present, can be a wide variety of other colors. For example, the yellow stones in this brooch are also sapphires. And in fact, sapphires are found in shades of pink to orange, even green. Now the large crystal that I have right here is also a gem material. It's the mineral known as topaz. And this is the crystal, the shape of the crystal as it comes out of the ground. And if you were to cut a gemstone from this crystal, you might get something that looks like this. This is a 2,000 carat topaz from Brazil, and typical of the color of most topaz crystals. Now you might think, not a particularly beautiful color. I mean, it's a big gem, it's kind of thing, make a big pendant, big ring. Actually, it makes a very nice museum display object, but the color is not particularly attractive. And if this was the only color you ever found topaz in, clearly it would not be a very popular gemstone. However, we can take crystals such as the one here and a gem such as this one, and we can treat it to change its color. And what we can do is we can irradiate it, that is, put it into a nuclear reactor or linear accelerator, then heat it, and that two-step process results in the topaz changing color to this lovely blue color. Virtually all of the topaz gems being sold today are blue, and the blue gems are in fact almost all irradiated and heat treated. There are virtually no natural blue topazes that get used in jewelry. So we can have a gem that is colorless and get its color by treatment. Also, topaz does come in other colors. Probably the most prized color of topaz is the so-called imperial golden color. This is a natural color. These ear clips show imperial topaz from Brazil. Imperial topaz such as this was especially popular in older pieces of jewelry, but you still see it in very nice pieces of jewelry today. Now you may think that this is a pretty good sized topaz crystal, and it's a nice sized crystal. However, if you would like to go with me now out into our new mineral gallery, we'll have a chance to take a look at some topaz crystals that are several times the size of this one, with one in fact weighing in at over 100 pounds. Well, here we are in the National Gem Collection Gallery looking at our big gigantic whopper of a topaz crystal. This topaz crystal in fact weighs 111 pounds, and this is the natural shape and form of this topaz crystal as it was found in Brazil. Typically, crystals such as this don't last very long because they're broken up and then cut and faceted into gemstones. So it's rather unusual to see a crystal this size and this perfection preserved. This crystal almost didn't make it here. This crystal, when it was found, was sold to a scientist in Boston who was going to cut it up and use it in scientific experiments. And fortunately, just before it was supposed to be cut, a better material was found for the experiment and the crystal was preserved. Eventually, the crystal was donated here to the Smithsonian so all of our visitors can enjoy seeing one of this world's great big topaz crystals. Now, in addition to topaz, we have some other very important gemstones here in the National Gem Collection Gallery. One of the most popular being emerald. Emeralds, of course, are a gem variety of the mineral beryl. And in the center of your screen right now, you can see a natural emerald crystal. This is about 800 carat crystal from Colombia. The best emeralds do come from Colombia. The necklace on the right is 168 carat emerald, and the necklace on the left is what we call a cabochon, or Baroque style emerald necklace. So emeralds are a variety of beryl that get their color because of trace impurities of chromium in the atomic structure. Now, if instead of chromium, as we've talked about, if we get a little bit of iron in the atomic structure, Then we get a different color of beryl. We get a bluish color, which is known as the gem aquamarine. And the large crystal to the left is an aquamarine crystal from Brazil. This is a very beautiful crystal and could be cut into many fine gems, such as the 1,000 carat gem aquamarine in the lower right-hand side of your viewing screen. Okay. Probably the most valuable gem, at least to most of us, is the gem diamond. Now, we saw the Hope diamond, which was a large blue diamond, but in fact our largest diamonds are in this case. The diamond to the left offers us a very special opportunity to see a natural diamond crystal. This is the way they're found in the ground before they're cut and polished. And this diamond crystal is 254 carats in size. This is the largest diamond in the national collection. This crystal shows the very typical octahedral shape. It looks like two pyramids, like the pyramids in Egypt, stuck base to base, and that shape is typical of most natural diamond crystals. Now, a crystal such as this one, if it were completely flawless and colorless, could be cut into a great gemstone, such as the diamond gem to the right. The gem to the right is the Portuguese diamond, and it's our largest cut diamond and one of the world's great and most famous cut diamonds. It's 127 carats in size. Despite the name, we find now it has no connection to Portugal. In fact, this diamond was found in South Africa in 1910. It was owned by Peggy Hopkins Joyce, one of the Ziegfeld Follies girls, one of the glamour girls of the 1920s, kind of the Madonna of her day. And she loved to have fine jewels and wealthy husbands, and so she ended up with a diamond like this. Eventually, it was purchased by Harry Winston and donated to us at the Smithsonian. Now, this diamond has a very interesting property. You can see it looks colorless in normal light, but if we take an ultraviolet light, sometimes known as a black light, and shine it on the diamond, we see that the diamond changes color, and in fact, we now see it shows a very deep blue color, and that blue color is a property called fluorescence. Fluorescence results when certain materials are exposed to ultraviolet light. The ultraviolet light interacts with the atoms in the structure of the material and causes visible light to be given off, in this case in the form of blue light. So that process is then fluorescence. About 15% of all diamonds will fluoresce. This being a large diamond shows a particularly spectacular fluorescence. Now we have another gemstone here in the National Gem Collection Gallery that has an equally interesting optical phenomena, and that's the famous Star of Asia sapphire. This sapphire is from Burma, and you can see that it shows on the surface of the sapphire a six-rayed star. Well, what is the reason for that star? It goes back to the early history of when that corundum crystal, when the sapphire crystal was first beginning to form. It was forming at fairly high temperature, typically forms when sort of dirty clays and limestones get squeezed and heated up. As the crystal was growing, the aluminum and oxygen atoms are connecting together to form the corundum crystal, and a few impurities of titanium also got trapped in the corundum crystal. Well, at high temperature, that's not a problem. But as the crystal starts to cool down, it starts to shrink or contract. And as it does that, the larger titanium atoms start feeling kind of snug, kind of tight in that corundum crystal. And the way they get around that problem is all the titanium atoms come together to form their own crystal of another mineral inside of the corundum crystal. So we end up with rutile crystals, that is titanium oxide inside of the corundum. These rutile crystals are long needles or fibers, and because of the symmetry of the crystal structure of the corundum, those rutile needles are forced to line themselves up in one of three directions. And we have, therefore, three sets of very fine rutile needles oriented inside the corundum crystal. And it's the light reflecting off of those three sets of rutile crystals that produce the star. Just as we show in this model that has, instead of three sets of rutile crystals, three sets of nylon fibers, sort of like fishing line, strung at 120-degree angles to each other. And you can see when light is reflected off of that screen, we get three bands of light, one off of each orientation of fibers in this case, that intersect to form a six-rayed star. The same thing happens in the Star of Asia, except instead of nylon fibers, it's long rutile crystals, and the light reflecting off of it produces the star. So, Sorena, do we have any stars out there that have any questions for us about anything we've talked about so far?
Hey, Jeff, we have an email from the Burris Lab School in Muncie, Indiana. The question is, can a diamond change colors after it has formed? I want to send that back to you, Jeff.
Me? Okay, Sorena. Yeah, I can try to answer that question. Can a diamond change colors after it's formed? Well, in fact, diamonds can sometimes change color, typically as the result of radiation. Either natural radiation, we think most green diamonds, for example, form because of the natural radiation in the rocks around where the diamonds are forming. So they may start out as colorless diamonds and eventually acquire a green color as they're radiated. We certainly know that diamonds can be artificially changed in their color by exposing them to radiation in the laboratory. And that's one of the problems now in trying to understand which diamonds, colored diamonds, are natural and which ones have been artificially enhanced, because many green and pink diamonds that are sold today, in fact, have been enhanced by laboratory treatment. So yes, a diamond can change color.
Okay. I'm going to go to the web page and have a look at some images from our archives. We've got a lot of things to do here. And let's take a look at some pictures. Where are they? Let's find the little dears. Oh, there they are. Here, the diamond archives. Since we've been talking about diamonds so much, I thought maybe it would be a good idea to take a closer look at some of these beautiful big diamond crystals, like the Oppenheimer diamond. This one shows off its pyramidal, bipyramidal shape to great effect. We'll go back and take a look at a couple of colored diamonds. Let's see if we can find those. Here we go, a red diamond and the blue heart. This is not the Hope diamond, but another blue diamond in our collection. I don't know if you folks out there have tried the web page, but it really is a good way to see our specimens a little bit closer up. Now, do we have any questions from Stark County?
Yeah, I have a question for you.
Sure.
What determines if a mineral is classified as a gemstone?
Well, it depends on a lot of things. Some gems in certain cultures are not gems in other cultures. For example, jade is as valuable as diamonds to many East Asian cultures, and yet we kind of consider it as sort of semi-gemstone, whereas diamond seems to have durable value across a variety of cultures. So value is something you place on it. But again, rarity, toughness, and beauty are three criteria that people use to decide what they want to be a gemstone. Hey, I think it's time to have a look at the great diversity of the mineral kingdom with our with a new host, Dr. Michael Wise. Mike, are you out there? Mike, you picking us up?
Yeah. Yes, I can.
All right.
Hi, Sorena. Welcome to the Mineral Gallery. KB and I was just looking at some of the many minerals in the display cases here, and one of the things that we've noticed is that there are a lot of minerals in the world. In fact, there are almost 4,000 different kind of minerals that have been studied in great detail by scientists all around the world. Now, some of these minerals are very, very common. Some are very, very rare. I would say that most of these 4,000 minerals are quite rare. But there are a handful of minerals which are very common in the Earth's crust. One of these mineral groups is the feldspar group. These minerals contain atoms of oxygen, silicon, aluminum, and some potassium, calcium, or sodium. Another very common mineral is quartz. And some of us might be familiar with quartz because quartz is common in our everyday beach sand and in the soil in our gardens. Take a look at the case here. We have a wide variety of quartz, which comes in lots of colors and sizes, and they range from colorless to purple to pink to dark black. KV, you have a question?
Yes. Why, if they're all the same minerals, some of them come in different shapes? Like the pink one is kind of smooth, but this one is like different rocks stuck together.
Well, that's a good question. The reason that they're different looking is because of the conditions under which they grew. Different minerals will grow in different ways based on the pressure and the temperature and the chemical composition of the fluid or the gas in which the mineral is growing. And so all of these factors play a very important role in the type of mineral that you get, but also in the shape and the size and the color of the mineral that you get. So minerals are very important to us in our everyday lives, and they're the building blocks of the universe. Sorena, does anyone have questions out there about minerals?
Have we got a question in on our toll-free number?
Yes.
Manual High School? Are you there?
Yeah. Us kids at Manual High School would like to know how much is the Hope diamond valued at or worth? And what is the biggest gem or diamond, and where was it found?
Okay. I'm going to bounce these to our diamondologist, Jeff Post. Jeff, how much is the Hope diamond worth, and what is the biggest diamond known?
Okay, Sorena, the Hope diamond is one of a kind, and so the best answer to what it's worth is it's priceless. We really don't know what it's worth. We could only know if we ever put it up for auction, and we're not going to do that. But it certainly is considered to be one of the most important diamonds in the world. And what is the largest diamond in the world? Well, the largest diamond in the world currently is a diamond known as the Brown Jubilee. It belongs to the King of Thailand, and it's about 550 carats in size, so more than 10 times the size of the Hope diamond.
Thanks a lot, Jeff. Do we have any questions from Stark County? Stark County? BJ?
Hi.
John?
John, I have a question about gems. How many different types of gems are there versus the number of minerals in the world?
Oh, that's kind of a toughie. Some gems, some individual minerals like beryl have 3 gems: aquamarine, emerald, and heliodor. So obviously not every mineral has a gem variety. So I think it's probably safe to say that there are fewer gem varieties in the world than there are mineral varieties, since we know of about 4,000 minerals. Isn't that right, Mike?
That's correct, Sorena.
Okay. Can we go back to Stark County?
What determines the value of a gem?
What determines the value of a gem? It's generally the rule of thumb is what someone's willing to pay for it. Do we have any questions from Washington, D.C.? Okay.
Can a few atoms being so minute produce a color that's spread throughout the whole stone?
Okay, the question here is, how can a few atoms being so small and so dispersed make color? And that's a really good question, and it's something we'll be talking about a little later in our program in great detail. Right now we're going to move into the wonderful world of crystal shapes. Jeff, are you there?
The National Mineral Collection Gallery, and I'm surrounded by beautiful minerals with beautiful crystal shapes. And crystal shapes have fascinated people for thousands of years. In fact, we know that even back as far as the ancient Greeks, they were fascinated with the perfection, the geometric shapes of crystals. And in fact, crystals have been the subject of a great deal of study for hundreds and hundreds of years. People trying to understand what makes crystals different than almost everything else you find in nature. For example, this group of quartz crystals is something that looks very different than anything else you find in nature. It has a perfection, a geometric shape that looks very different than a tree or a plant or an animal or things like that. So crystals have fascinated people for a long time. You want to know what in the world makes a crystal. Well, I've got a couple of young crystallographers here that are going to help me figure out what we know about crystals and why. We've got Daryl and we've got Kristen, and we're going to repeat a couple of experiments that were done in the 1700s that helped us to learn about crystals. And I think many of you will have an opportunity to do this experiment in your classrooms as well, and so you can follow along with us. Well, the first experiment that we're going to do involves the mineral quartz. Quartz is one of our most common minerals, and crystals of quartz are found in pretty good size in a lot of places around the world. And there was a fellow by the name of Nicholas Steno in the 1600s who started looking at quartz crystals from all over the place. And when he started to take these quartz crystals and to measure the angles between the faces of the quartz crystals, he found that no matter where he did that, no matter which quartz crystals he measured, the angles were always the same. In this case, 120 degrees. Well, that implied some regular order in these. Now let's see if in fact that's really the case. Okay, Daryl, Kristen, we're going to ask you guys to do the same experiment that Steno did. Let's take some quartz crystals. Now, if you look at a quartz crystal, it looks a little bit like a stubby pencil. And it comes to a point. It's got flat faces around the side. So if you think of this as a stubby pencil, it's the faces around the sides of the pencil that we're going to be measuring the angles between those faces. So go ahead, let's see what we got here. If we measure, okay, Daryl gets 120 degrees. Well, that's pretty good so far. Kristen, what do you get? 120 degrees. So try this one, see if that one works. Okay, this is certainly an experiment you could try at home. And 120. So what Steno found and what Daryl and Kristen found here is that regardless of which quartz crystal you take, no matter where it came from, we always get the same angle. This implied there's something about the internal structure of quartz that's very orderly, very regular, and it's happening the same way for all of the quartz crystals. So, now another experiment that happened, and this is an experiment that really was kind of an accident and then turned into an experiment. There was a Frenchman by the name of Aui who was looking at his friend's mineral collection, and he had a calcite crystal, something like this, and was holding it, admiring it, and he dropped it to his horror. And when that crystal dropped and hit the floor, it broke into bits, many, many bits and pieces. But as he was picking up the pieces, he found something interesting. Now let's see if we can repeat that experiment. Now we're not going to smash this on the floor. Instead, we're going to do it in a much more dramatic fashion. We're going to take this calcite, and we're going to have Daryl and Kristen smash it right here before your very eyes. Now again, I think many of you have calcite crystals in your classrooms, and hopefully a hammer. And I would suggest taking your crystal and putting it perhaps in a cloth like this one. Now we'll see if these guys got enough strength here to beat this thing into pieces. Go ahead, just bang at it. Oh, harder than that, come on, beat. Oh, there you go, good. Daryl, give it a few whacks too, come on. Whack that thing. Whoa, all right, Daryl, yeah. Okay, well, as you can see, they did a pretty good job breaking this into lots of little bits and pieces. Now, take a look at some of these bits and pieces, and you'll notice, as you pick them up, that they all have sort of a distorted cube or square shape. It's kind of an egg. And all the pieces look pretty much the same shape. What Aui found was that he reasoned that all of these little pieces suggested that crystals are made up of building blocks that all have basically the same shape. And if you stack them together in an orderly way in 3 dimensions, kind of like bricks in a wall, you can build up a crystal large enough to see. We know now that the building blocks are in fact atoms. And for example, in the mural behind me, these atoms are sodium and chlorine atoms that make up the crystal structure of salt. And it's the orderly repetition of atoms in 3 dimensions that makes something a crystal, hence the perfection and the geometric shapes of a crystal. Daryl, Kristen, you're great crystallographers. Thank you very much. I think we proved the point here. Okay, Sorena, back to you. You smashing crystals back there?
No, but I understand we have a call on our 800 line. Go ahead. Where are you from?
Where
are you from? Where are you calling from?
Burris.
Where are you calling from?
Indiana, Muncie.
Burris Middle School, Muncie, Indiana. What is your question?
What is the most unusual color you have ever seen in a gem?
What is the most unusual color you have ever seen in a gem? Well, my personal unusual color is a gemstone that actually shows 2 colors, one in sunlight and one in room light. It's a gem called alexandrite, and because of its unusual chemical composition and the fact that human eyes detect sunlight differently than they detect room light, the 2 different light sources actually have the gem turn from green to red to green to red, depending on the light source. I wanted one for my engagement ring, but at the time it was $10,000 a carat. So it's obviously a very rare as well as a very unusually colored stone. Next question. How about one from Stark County? Devin?
Why are all the crystal angles the same even if you smash it up?
Why are the crystal angles the same even if you smash it up? Well, it's the thing about atoms is that they're much, much smaller than the scale that you're smashing this crystal up. In fact, you couldn't really, with a hammer, divide a crystal anywhere near the level of its atomic structure. And because the cleavage, these are the breaking points of the crystal, as well as the external shape of the crystal, are both controlled by its internal atomic structure, you can never get down to the level where you would be breaking the essential structural element apart in a crystal. And that's why these geometric rules stay true. You can't break through the bricks in the wall. You can only break along the lines of the bricks that have built the wall. Okay, it's time for us to go and learn a little bit about color. And I think that's Jeff. Are you there?
She's just, okay. Well, I'm now in a very colorful part of our exhibit, surrounded by colorful minerals. Just imagine if all of our gemstones were in fact colorless. It would be a pretty boring world. Well, fortunately, that's not the case. Mother Nature's done a great job of coloring minerals and crystals for us. And the reason we see color in minerals and gems is the same reason that we see color in anything else, in flowers, in your clothing. It's the way that light interacts with the atoms in their structures. Certain atoms will absorb certain colors of light. We know that visible light is made up of all the colors of the rainbow, and if certain colors are absorbed, then only the colors that remain are reflected back to our eye to see as color. For example, I'm standing in front of a case of minerals that are all shades of blue and green. All of these minerals are colored by copper. And in fact, if you're searching for a copper deposit, looking for blue and green stains on the rock would be a really good way to do that. Why are these minerals all shades of blue and green? Well, it turns out that copper atoms absorb light in such a way that we have all the colors being absorbed by the atoms, and what the light that actually passes through the structure and reflects back to our eye is the only color that's not absorbed, which are the shades of blue and green. So copper atoms produce shades of blue and green typically. Now I've got one other group of minerals here that are prized because of their many different colors, and that's the mineral corundum, which we've talked about a little bit previously, recalling that it's impurities in this case that give us the various colors. In the case of ruby, we get the chromium impurities that give us the deep red color. And so let's look in some detail now at what happens when light interacts with the chromium atoms in a ruby crystal and why it is we see the color that we do.
Why is a ruby red, an emerald green, and a sapphire blue? It starts with light, which is made up of all the colors of the spectrum mixed together. Watch. A prism placed in front of a beam of visible light separates the colors so that you can see them. You see an individual color only when some of the other colors are removed. Now you see blue because this filter absorbs all the colors except blue. Like a blue filter, some crystals absorb certain colors of light. A sapphire appears blue because it absorbs all colors except blue. And a ruby appears red because it absorbs all colors except red. What happened to the other colors? To find out, we need to look deep inside the ruby. Ruby is a variety of the mineral corundum, which is made up of aluminum and oxygen atoms. In its pure state, corundum is colorless. But every now and then, a few chromium atoms get trapped as impurities by a growing corundum crystal, producing a ruby. What special power do these atoms have to color a crystal red? It has to do with how they interact with light. Like all atoms, a chromium atom consists of a nucleus surrounded by electrons. The electrons whirl about in different energy levels. If a particular color has the right energy, it can kick an electron to a higher energy level. That color is absorbed. chromium atoms have electrons that absorb yellow, violet, green, and some blue light. Only the red light is able to pass through unabsorbed to your eyes. As long as light shines, the electrons are kept busy, hopping up and down, absorbing light and producing color. And that is why the ruby is red. The same general process is at work in all minerals, and in fact in all things that have color. Thanks to all those busy electrons, we live in a very colorful world.
Hi, North Montgomery High School. What is your question? I understand we have an 800 call. Is that correct?
Is there any particular color of diamond or mineral that is more valuable than others?
Well, it really depends on the mineral. Of course, a blue diamond is very rare. I believe that the rarest of all diamonds are red, and we have a beautiful red diamond on our archives in our webpage for you to take a look at. Do we have any questions from Stark County?
Yes, I have a question. Is it possible to change the color of the mineral when you change the angle of reflection?
Only in some minerals that is the case, and it is a property of some minerals, but not all of them. Hyde High School, you're on the air. What is your question?
Could you explain how the quartz in clocks works?
How quartz? Could you repeat the question, please?
Could you explain how quartz in clocks works?
Can I refer that question to you, Jeff? Okay, Jeff, will you take it?
Yeah, quartz is a mineral that we use every day in our watches and our clocks, and it's because of a very special property that quartz has called piezoelectricity. That is, that when you apply an electric charge to a quartz crystal, it starts to vibrate. And so they've figured out by cutting a quartz crystal, and usually there's synthetic quartz crystals in watches now, but by cutting it just the right thickness and then applying an electric charge from a battery, for example, they can make that quartz crystal vibrate at exactly the right frequency to keep very accurate time.
Thanks, Jeff. That's great. Let's go to our webpage and take a look at another interesting variety of silica. It's opal, which seems to have every color in the rainbow right inside a single cabochon. Jeff, I understand that you're going to tell us a little bit about the story of color in opal. Are you there?
Okay, Sorena, you're getting some great questions. Well, in fact, some of the most interesting questions that we've been getting since the new hall has opened have to do with opals. People are fascinated by opals. And obviously it's a gemstone that's a little unique. It's different than most other stones because typically it's not worn as a faceted gem, but rather is appreciated for its beautiful display of flashing colors, like the ones that I'm showing here. Opals are the only gemstone that we have that show this kind of flashing of rainbow colors. And so the question that comes up so commonly is, why do opals show this color? What is the mystery? What is the story behind opals? Well, opals are a fascinating material. They're basically silica, that is silicon and oxygen, and a little bit of water thrown in. And it's been a long time, for a long time, it was really a problem trying to sort out what was the source of the color in opals. And it really wasn't until, about 15, 20 years ago, after the scanning electron microscope became an important tool in studying minerals, that the answer finally was resolved. And when scientists in Australia took an opal and looked at it closely under the scanning electron microscope, what they saw was that opals are made up of very tiny little spheres of silica. And they're stacked together pretty much the way you'd see oranges stacked up in a grocery store. And it's the stacking of those spheres in a very orderly, regular way that interacts with the light hitting the opals, causing the light to be diffracted or broken apart into its various colors of the rainbow. And if an opal has a very orderly arrangement of these silica spheres, then you get a very nice play of colors, like the ones here, or many of the opals that we see here in our display case. And some of the very finest opals today come from Australia. The opals that have a darker colored background, sort of a grayish background, are referred to as black opals and are by far the most prized of the opals. Opals with a whiter colored background, such as the one here, are called white opals and also are very popular in jewelry. Nowadays, most of our very fine gem quality opals come from Australia. And that's really been the case since the late 1800s. Prior to that, the only known source of opals was in Eastern Europe, in a portion of Hungary that is now, in fact, part of the country Slovakia. But with the development of the opal fields in Australia and the huge number of really beautiful opals that were being produced, opal quickly became a very popular gemstone. Now, we normally don't think of opals as being a gemstone from the United States. However, there is one locality in the western part of the United States that produces some of the world's most beautiful opal. And that's the dark colored opals that you see in the upper left-hand portion of this case. And those opals come from a place called Virgin Valley, Nevada. And this opal formed as a replacement of tree limbs. The trees died, the limbs fell down into a small pond or lake, were covered by volcanic ash, and then later on, water-carrying silica circulating through replaced the tree material with silica in the form of opal. And the opal is a spectacular opal, beautiful play of colors. The only unfortunate thing about this opal is it tends to contain a fair bit of water, and when it dries out, it cracks or crazes. And because it's a fairly unreliable opal in jewelry as a result of its cracking, jewelers have tended to shy away from it and instead prefer the Australian opals. So it's beautiful as specimens and display cases, but unfortunately not an opal that's generally encountered in jewelry pieces. Now, opal in general has a bit of a reputation, or at least it used to have, of being a stone that's bad luck. Now, why would that be? Well, it turns out that, first of all, there were a couple of stories written in the early part of this century that featured the main character having an opal as a major gemstone, and this main character then had a fair bit of bad luck, and as a result, people started associating opals with bad luck. Also, because sometimes opals do tend to dry out and crack, because they are somewhat brittle in jewelry, people would have mishaps with their opals, or because they weren't reliable sometimes in their jewelry. That started to support also this idea that they were bad luck, that people just had unfortunate occurrences with them. Fortunately, that story seems to pretty much be one of the past. Opals today are extremely popular in jewelry, and as a result, prices for good opals are very high today. Opals are an example of a mineral that typically do not form good crystals. As we said, they're made up of these tiny little spheres of silica, and we never find big crystals of opal. They tend to occur as seams in rock or as coatings on a rock surface. However, we do have in the gallery other minerals that show some very marvelous examples of beautiful crystals. And let's go take a look at some of those now. Okay, here are some examples of very well crystallized minerals. For example, the cerussite here and the gypsum specimens that we see. One of the things that sometimes people have a hard time thinking about is thinking of crystals as growing. And in a sense, crystals do grow the same way that plants and animals grow. And they grow as atoms add on one after another, building up a crystal. And sometimes if the growing conditions change, the crystals, even crystals of the same mineral, can look very different. For example, we have gypsum crystals here. We have very large blocky crystals of gypsum, and we have this sort of a curlicue looking gypsum specimen. Different growth conditions give rise to different crystal habits. Now, another mineral that also shows quite a variety of different crystal habits because of the different growing conditions is calcite. Let's take a look at some calcite specimens up close. We've been talking about how crystals grow as atoms lock into place, forming a regular, orderly repeating pattern. But there's more to the story of crystal growth. Crystals also depend upon the conditions under which they're growing. And a good example of that is with the mineral calcite. Calcite is a common mineral. It makes up the rock we know as limestone. It has a very simple chemical composition, calcium carbonate. However, depending upon the conditions under which it grows within the earth, it can show itself off in a tremendous variety of different crystal shapes. In fact, calcite shows more different crystal shapes than any other known mineral. Now, why is that? Why is it the same mineral can show many different crystal shapes? All of these specimens of calcite have the same atomic structure, same arrangement of calcium and carbonate. However, you can see they look very different. For example, the large crystal here in the center of the case is known as a dogtooth crystal. It comes to a sharp point like a tooth. In the upper left, we have a flattened crystal. The miners nicknamed these crystals poker chip crystals. And to the right, we have this lovely pink crystal. It looks kind of sugary. Those are called rhombohedrons. Very different looking shapes. So how is it that one mineral can look all these different ways when it forms its crystals? The shapes of the calcite crystals depend on a number of different growth conditions. For example, the temperature under which they're growing, the concentration of the solution from which they're growing, that is, how many atoms of calcium carbonate are present in that solution. It also depends upon the composition. It may depend on whether impurities are present in that solution. All of these different factors come together to influence the shapes of the crystals. Crystals are very sensitive to their growth conditions. So for example, one thing we know about calcite crystals is that these long dogtooth-shaped crystals, called scalenohedrons, tend to form under conditions of fairly high concentration, a lot of calcium, a lot of carbonate in the solution. Other crystals in this case we know tend to form under conditions of fairly low temperature, that is maybe about room temperature. If you heat the solutions up, the crystal shape will change. And in fact, many times on the same specimen, you will see crystals that show 2 or 3 different shapes. And clearly that's an indication that the growth conditions were changing rapidly as this specimen was forming. So crystals are a great way to learn something about the growth history of a specimen. By simply looking at the shape, very often we know then something about the temperature, the concentration, the composition of the solutions from which it was growing. Now in the case of calcite, we're seeing that there were many different kinds of growth conditions by looking at the shapes of the crystals. Another way to learn something about the sensitivity of crystals to its growing condition is by looking in some detail at the internal structure of the crystals. If we wanted to look at the growth history of a tree, for example, one way to do that is to cut a slice right through the trunk and look at the tree rings. They can tell us periods of time when perhaps the tree was growing real well or when it was experiencing a drought. Well, similarly, we can look at the growth history of a crystal by cutting a slice through a crystal. Or in the case of this particular crystal, we've cut it into many slices. And by looking at the color, the composition, the structure of the crystal as revealed by these slices, we can tell something about its history. For example, in this case, we can see that the crystal started out as a purple crystal. And it was purple because the solution from which it was growing was enriched in manganese. But as the crystal continued growing, the composition of the growth solution changed, became more iron-rich, and as a result, the crystal changed to yellow. So the end result is a crystal that's purple on the inside, yellow on the outside. By looking at these changes in color, changes in composition, it allows us to put together the story of this particular crystal. Now, let's go to some students who are looking at some other crystals that have equally interesting stories to tell us.
Yeah, we're looking right now at a beautiful crystal of tourmaline from Maine. This tourmaline contains boron, a very rare element, as an essential part of its mineral structure. This mineral grew in an unusual environment known as a pegmatite, where crystals not only grow beautifully, they grow very, very large. And I think that Mike Wise is going to give us a tour of the wonderful world of pegmatites. Mike?
Actually, Sorena, we're going to me, I guess, right now. Back.
Okay, forget the pegmatites.
Well, actually, I'm in pegmatites too, but I'm looking at one particular mineral, the one that you were just showing, which is tourmaline. And we've got here 3 of our most spectacular tourmaline specimens in the collection. These are tourmalines from Brazil and from California. And what I wanted to talk about here is why tourmaline is useful to us. Besides being beautiful crystals, which can be cut into gems, tourmaline also has a very interesting history. In fact, during World War II, tourmaline was considered to be a strategic material, and it inspired quite a smuggling trade to get enough tourmaline crystals into the United States to support the war effort. So what was tourmaline used for? Well, tourmaline, like the quartz we talked about a little bit earlier, has a property known as piezoelectricity. If you apply pressure to it, it actually produces an electric charge. And so what the tourmaline crystals were being used for was to make pressure gauges that could be used to measure the intensity of explosions. And in fact, the intensity of the first atomic bomb explosion was measured using a tourmaline pressure gauge. The pressure of the explosion hitting the tourmaline crystal in the gauge would set up an electric charge, and a meter would measure the intensity of that electric charge. Therefore, would tell you the intensity of the explosion. We use tourmaline crystals today also. In fact, most of you probably use them at home many times a year, especially if you've got a gas stove or a gas barbecue grill with an automatic starter on it. The starter, when you press the starter button, applies pressure to a small crystal of tourmaline in the starter, and that pressure causes a spark to be produced from that tourmaline crystal that then ignites the gas and the grill or your stove. So tourmaline, in fact, is a very useful mineral to us. Now, tourmalines form in special kinds of deposits known as pegmatites. And I'd like to turn you over now to Mike Wise, or as we know him here as Mr. Pegmatite, who will tell you everything you ever wanted to know about pegmatite deposits. Mike, let's hear about pegmatites.
Thanks, Jeff. Well, pegmatites are very unique kind of rocks. In fact, I like to think of them as nature's giant treasure chest. The reason why I think of them that way is because if you look at most rocks like a granite or a basalt or any volcanic rocks, and you look at the crystals, you notice that they're very, very tiny. Some are almost microscopic. Well, pegmatites are unique in that the crystals that grow in pegmatites are very large, almost gigantic. This crystal that I'm sitting on is part of a beryl crystal, and this section is about a little over 3 feet long. But the entire crystal was on the order of 10 to 18 feet long. This is still not a record. In fact, the largest crystal ever reported from a pegmatite was on the order of 50 feet long. And so the thing that really characterizes pegmatites are the giant crystals. One of the other unique features about pegmatites is the fact that you have this wide diversity of minerals. And if we look in the cases to my left, you'll see a wide variety of very rare and exotic minerals, minerals that you normally wouldn't see in other rock types. Now, a lot of these minerals are really special in that to form these minerals, the pegmatite process concentrates a lot of rare elements. And these rare elements concentrate to a point that they can form exotic minerals like lepidolite and spodumene and cassiterite. The other feature that's very unique about pegmatite is that when conditions are right, they can form minerals that are gemmy enough to be cut into gemstones. Take a look at the topaz case here. Jeff talked about topaz already. Well, these very large topaz gemstones you see came from topaz crystals that came out of pegmatites. And so this is why I like to think of pegmatites as nature's giant treasure chest. Sorena, do we have any people out there who want to join me out in the field collecting pegmatites?
Anybody? Anybody want to come along? Yeah, we have some volunteers from Washington, D.C. Do we have some questions about pegmatites? Yeah, pick up the mic and fire one off.
Where are they found? Like, I mean, are there any special place in the world or any type of environment that they're found in?
Did you hear that question, Mike? Are there any special places in the world where pegmatites are more abundant or are commonly found? Mike? We don't have Mike? Well, yeah, there are. Pegmatites, because they're associated with granites, tend to occur in 2 different settings. One, places where lots of granites are in place. These are at the margins of continents. And 2, in very ancient terrains where sediments have actually been buried so deeply and for so long that they began to melt and generate granite. So that the 2 ways that you generate granite are also the 2 ways that you get pegmatite. We have a telephone call from Magoti High School, you're on the air. What's your question?
Yeah, can coal turn into diamonds?
Turn your mic down, guys. Turn your TV set down. Down. Try again.
Yeah.
Okay? You there? Try again.
Can coal turn into diamonds?
Can coal turn into diamonds? That's the $6 million question, isn't it? Well, coal is a hydrocarbon. It's carbon bonded to a lot of hydrogens, and it is a mature type of plant material. Now, the interesting thing about coal is that it has the potential to turn into diamonds because it has carbon in it. If the coal were taken down on a downgoing slab deep into the mantle and to a place where pressures and temperatures were appropriate, it could indeed be turned into diamonds. But the evidence for this process actually having occurred is very, very limited. So we don't actually have any direct evidence for coal having been transformed into diamonds. But one other interesting point about that is that in the early days, when experimental petrologists tried to turn things into diamonds, it's rumored that a guy at Bell Labs took a peanut butter sandwich, burned it up, put it in his high-pressure lab, and did make teeny tiny little diamonds out of it. So everything that's got carbon in it has potential. Burris Laboratory School, question? Have we got a question from you? Ask again. I think we've got a technical difficulty. Can we take a question from another 800 number? Or Manual High School? Manual High School, have you got a question? Burris Middle School, are you there?
Yeah.
Okay, what's your question?
Have you ever found a gem or diamond with more than one color in it?
A gem or diamond with more than one color in it? Well, the gemstone tourmaline commonly has a number of colors in it, and some jewelers take advantage of that by cutting them along the directions of color changes to get pretty plays of green and pink in the same gemstone. Those are called bicolor stones. Next question? Any more questions? To Jeff? We're going to go over. Okay, Jeff, I hear that you've made it all the way to the mine.
Okay, we're on.
Speaking of gems and ores and valuable things, can you come in, Jeff?
I'm here, Sorena. In fact, welcome to our Smithsonian mine. We have a mine built here in the Museum of Natural History, and it's a very special kind of mine that it shows several different kinds of ore deposits from around the United States. Now, why would we build a mine? Well, what we're trying to do is, first of all, give our visitors a chance to see what some of these minerals actually look like underground, where most of them are found. Most of our minerals that we've seen today and that are in our galleries actually are the result of a mining operation somewhere. And of course, also to remind us that minerals are very useful to us. In fact, any mineral that can be mined and is useful and can be mined for a profit is referred to as an ore. And I have an example of one here from Missouri. This is very typical of the minerals that are mined in the central part of the United States. And the cubic-shaped crystals here are the mineral galena. Galena is lead sulfide and is the major ore of lead. So this is what would be mined in this mine in Missouri. Now we also have another specimen from my assistant down below here. This is a large chunk of a mineral called celestite. And celestite, of course, comes from Ohio, is one of the common places where it's been mined. What would you mine celestite for? Well, it turns out celestite is a strontium sulfate, and it's an ore of strontium. Okay, what do you use strontium for? Well, anybody who's looking at a computer screen or who has watched TV today has made use of one of the properties of strontium in that it's used to coat TV screens to cut down on the amount of radiation that would pass into the room otherwise. Also, it's the red coloring agent in fireworks. So strontium is very useful to us. Now, a material that we all would recognize as being valuable if we were digging a hole in the ground to make a mine is, of course, gold. And we have a wide variety of gold specimens in the National Collection. These large leaf gold specimens are from California. California, of course, is the site of the great gold rush in 1849. The miners rushing to the state to try to find gold and pretty much putting California on the map. There have been other great gold rushes in Australia, in Alaska. Pretty much anywhere gold is found, it has a profound effect on the population and the civilization there. Gold has been valued for many, many centuries because of its color, its fact it's heavy. It's just considered to be a valuable metal. And today we still use it in jewelry and value it in the form of coins and bullion. But more and more gold has become a very important metal to our high-tech industry. And it's become important because gold is one of the best conductors of electricity. It also does not corrode. And therefore, it's very good material to use in electronics where you need good electrical contacts. So any of your computers, electronic equipment these days will probably have some gold in it. Now let's take a walk through the rest of our mine and take a look at what we have here in the Smithsonian mine. Okay, coming around the corner, walking through our mine tunnel, we have as one of our mines an historic mining district from southern Arizona, a place called Bisbee, Arizona. This is where the old cowboys and the gunfights and the whole bit took place back in the late 1800s. And what was the source of all the excitement there was the copper mining. This is the home of the famous Copper Queen mine, where most of the copper in the world was being mined in the late 1800s. And what we've recreated is one of the mineralized zones that was mined from the Copper Queen mine. You can see the deep blue azurite crystals, the deep green malachite. They're prized as mineral specimens, but in fact were the ore that was being mined in Bisbee. We also have here in the mine a special kind of a mineral deposit that is very well known in the central part of the United States. It's called a Mississippi Valley type deposit, and states such as Missouri and Oklahoma, Kansas, Illinois, Wisconsin, all are places where you can find these kinds of deposits and where they are mined typically for lead and for zinc. And so looking over here in our Mississippi Valley deposit, we can see a galena vein. Remember, galena is the main ore of lead. That whole sparkly zone that we're looking at is the actual galena vein. We went underground in the mine, collected that vein, put it back in place just as we saw it underground. And we've got it set up here for blasting just the way the miners would do it. They would fill those holes with dynamite, blast the ore out, take it to the surface, and then process it in a smelter to remove the lead in this case. So minerals are very important to us as ore materials, and by coming to the Smithsonian mine, you get a chance to take a look at what some of these things look like underground before they're mined. Okay, Sorena, are you ready for some questions?
I hear we have one last quick question from Tell City High School. You're on the air. Tell City High School?
Now?
Are you there?
Yeah.
Yeah? Can you ask your question, please?
How do you cut the crystal to make it form into a gem or gemstone?
It's not cut, it's polished into those beautiful geometric shapes. It's a complex process that involves adhering the rough gemstone to a stick and systematically polishing it against a rotating lap wheel, a wheel that has grit on top of it. It's something that people go to school for many years to learn, and it's a most exacting craft. All right, I think it's time
from underground. That's right, from the mine.
Come underground
right.
and come back to the surface.
And even here on the surface.
We have one last question. North Montgomery High School, you're on the air.
Yeah, we want to know how long it took to cut the topaz gem.
How long did it take to cut that big topaz gem?
Well, I don't know the answer specifically for that gem. However, we have some other topaz gems that are even a little bit larger than that one that I know in one case took the cutter about 1.5 years to cut it properly because of the size and the weight of the stone. He had to make some special equipment, and it's not something you just buy off the shelf. So he was able to build the equipment he needed to cut that large stone. So I would say typically a few months to In this case, a year and a half. It all depends. Larger stones are definitely much more difficult to cut and polish.
Stark County, do you want to get in one last question? Anyone in Stark County?
Are they awake over there?
Are you up? Are you awake?
Going to lunch.
Have you gone to lunch? Okay, Stark County.
I'd like to know what kind of process gold has to go through from when it's mined to where it's sold as in the form of jewelry.
What has to happen to gold between when it's mined and when it's made into jewelry? Mike,
The process.
What process? Refine. What process does gold have to go through between when it's mined and when it's made into jewelry?
Well, it's quite a long, extensive process. I don't have a lot of time to go through this, but essentially they extract it, they smelt it, and they use chemicals to float the gold from the ore material and skim it off the top.
Okay. I'm afraid that we've run out of time to describe gold. We have to get a quick summary in here. Here we are standing again at our billion-year-old rock, a rock that is
an ore.
An ore.
Is made of minerals.
Made of minerals.
That has a great story behind it.
That's right. This rock is a billion-year-old metamorphic rock from New York that's being mined for
the garnets, sandpaper, abrasives.
Yeah, we got nice big softball-sized garnets here, and it's one of the few places in the world where you actually have garnet deposits large enough that it actually can be mined.
So minerals become rocks, rocks become ores, and the most outrageous rocks that we know about are also the oldest ones on Earth, but they're not natives. And we have a specialist here who works with these alien visitors to the planet. Glenn McPherson, can you come in?
Thank you, Sorena. And now for a very different story. Most of the visitors, when they come to our Geology, Gems, and Minerals exhibit hall, come to see the Hope Diamond, which in addition to its famous beauty, also tells a story of how it formed deep inside the Earth long ago under conditions of extreme temperature and pressure. But these same visitors end their tour with a very different kind of diamond, which you can see in the case here to my right. These diamonds didn't even form on Earth at all. In fact, they formed long before Earth or the solar system existed. These diamonds formed during the cataclysmic explosion of a dying star, and they tell the story in part of how Earth and the solar system formed and when and why it formed. Interestingly enough, clues to how our planet formed are missing from Earth's own rock record because the geologic processing have destroyed those clues long ago. But we can learn about the origin of Earth and its solar system from looking at meteorites, which are bits of rock that fall to Earth. Mostly they come from the asteroid belt, and these rocks have been drifting in space for 4.5 billion years in cosmic deep freeze, and they preserve their clues to how the solar system first began to form and evolve. In the next electronic field trip in March, my colleague Tim McCoy and I will tell you about some of the fascinating stories that we can learn from meteorites about the solar system's formation and evolution. Back to you, Sorena.
Thank you so much, Glenn, and thanks to the students of Stark County, of T.C. Williams High, and come join us again March 10th for our next installment of A Gem of a Show.